Welcome to Mindful Moments. Nourish your mind on the go. Our AI narration lets you delve into the wisdom of timeless books, extracting those golden nuggets of insight. This time we're using The Elegant Universe by Brian Greene as our guide.
This book, it's really about more than just physics.
Okay.
It's about questioning what we think we know about reality itself and how much of that is just our limited perception.
Yeah, Greene really has a way of explaining these really complicated ideas so that anyone can understand them.
Exactly.
And he really makes you think about things in a new way, like space and time and the very fabric of existence.
Yeah, and right from the start, Greene kind of throws us into the deep end with this big conflict at the heart of modern physics,
Oh, yeah.
the clash between general relativity and quantum mechanics.
Okay, so we've got these two incredibly successful theories.
Right.
But they each explain different aspects of the universe. So where does that conflict come in?
Well, the problem is when you try to apply both of them to extreme situations,
Okay.
like black holes or the Big Bang, when you try to combine them, you get these nonsensical results,
Oh, really?
like infinities popping up in the equations.
Yeah. So they just don't work together.
Exactly. It's like you're trying to fit two puzzle pieces together.
Right?
That should work, but they just don't.
So does that mean that one of these theories is wrong?
Not necessarily. More likely, they're both incomplete.
Okay.
Like we're missing a crucial piece of the puzzle.
Interesting. So we're missing something big here.
Yeah, and finding that missing piece could completely change our understanding of the universe.
Like a revolution in physics.
Just like Einstein's theory of relativity did over a century ago.
Speaking of Einstein,
Yeah.
Greene does an amazing job of explaining how special relativity totally changed our understanding of space and time.
Yeah. It's one of those things that's really hard to wrap your head around.
Right.
We think of time as this constant.
Yeah, ticking away at the same rate for everyone.
Yeah, right. But Einstein showed us that time is actually flexible.
Okay.
It can be warped by gravity and motion. The faster you move, the slower time passes for you,
Whoa.
relative to someone who's stationary.
So time is relative.
Exactly. It's not absolute, like we might assume.
That's mind-blowing. And Greene illustrates this with that example of the twins.
Oh, yeah. One stays on Earth and the other travels at near the speed of light.
Right. And when the traveling twin returns.
They'll have aged less than the twin who stayed on Earth.
Yeah. And this time dilation effect,
Right.
it's been experimentally verified, too.
Yeah, with atomic clocks flown on airplanes.
It's just incredible.
It really challenges our whole perception of reality.
It does. And it's not just time that's relative.
You're right.
Space is, too.
As objects approach the speed of light, their length actually contracts in the direction of motion.
Really. So like a spaceship traveling at near the speed of light.
Exactly. It would appear shorter to someone watching from Earth.
That's wild. So our measurements of distance are also affected by our motion.
Right. Both space and time are kind of fluid and intertwined.
Forming this four-dimensional fabric called space-time.
Exactly. And that's where gravity comes in.
Okay.
According to Einstein, gravity isn't a force acting at a distance. It's a curvature in this space-time fabric caused by mass and energy.
Oh, I see. So like a bowling ball on a trampoline.
Exactly. It warps the fabric around it.
And that's how gravity works.
Right. And this curvature dictates the paths of objects through the universe.
Wow. From planets orbiting stars
Right.
to light bending around galaxies.
Exactly. It's all about the curvature of space-time.
And that brings us to another mind-bending concept.
Okay.
The idea that simultaneity is not absolute.
This one's a real head-scratcher.
It is. So what does it actually mean?
Imagine you're on a train platform
Okay.
and you see two lightning bolts strike at the same time.
At opposite ends of a passing train.
Exactly. From your perspective, they happen simultaneously.
Got it.
But for someone on the train,
Yeah.
those same events would appear to happen at different times. There's no universal now.
That's so strange.
The order of events can actually depend on your frame of reference.
So our perception of when things happen,
Right.
it's not fixed.
Nope.
It's relative to our motion.
Exactly.
So much of what we think of as reality is just a product of our limited perspective.
It's a humbling thought, isn't it?
It is. It makes you realize how much more there is to discover about the universe.
Absolutely. And this journey of discovery takes us from the vastness of space to the incredibly tiny world of subatomic particles.
Right. Greene reminds us that our understanding of matter has come a long way since the ancient Greeks thought atoms were the smallest things.
Yeah, we've discovered that atoms themselves are made up of even smaller particles.
Protons, neutrons, electrons.
And those protons and neutrons
Yeah.
are made up of even tinier particles called quarks.
It's like peeling back the layers of an onion.
Exactly, and it makes you wonder,
What are those fundamental particles ultimately made of?
right, is there a limit to how small things can get?
And that's a question that physicists are still trying to answer.
And it's one that string theory attempts to address.
Okay, so what exactly is string theory?
Well, in a nutshell, it proposes that the most fundamental building blocks of the universe aren't point-like particles, but tiny vibrating strings.
Strings like little pieces of string.
Yeah, vibrating at different frequencies.
And these vibrations determine the properties of the particles.
Exactly, things like their mass, charge, and spin.
So instead of a universe of tiny billiard balls, we have a universe of vibrating strings.
And that's the idea. It's a pretty radical shift in our thinking.
It is. So what led physicists to this idea?
Well, one of the big motivations was to unify gravity and quantum mechanics.
Right, that clash of the titans we talked about earlier.
Exactly. String theory offers a potential solution by incorporating gravity into a quantum framework.
Okay, so string theory could be the key to unlocking a deeper level of understanding.
Potentially one that could reconcile the worlds of the very large and the very small.
I'm definitely intrigued and ready to dive deeper.
Me too.
But I think we've covered a lot already in this first part of our deep dive. We've journeyed from the vastness of space to the subatomic realm.
Right.
We've encountered mind-blowing concepts like time dilation and the relativity of simultaneity. And we've even gotten a taste of string theory.
A lot to think about.
It is. In the next part, we'll venture further into the quantum realm and explore the bizarre world of wave-particle duality.
That's right. We'll grapple with the implications of these discoveries for our understanding of reality itself.
Stay tuned, folks. It's about to get even more mind-bending.
Welcome back to our exploration of the elegant universe. We've been talking about the clash between general relativity and quantum mechanics, and how string theory might be able to bridge the gap between those two seemingly incompatible worlds.
Yeah, it's a fascinating idea.
But before we go too deep into string theory, let's take a closer look at the quantum realm itself, a realm that really challenges our everyday intuition in some pretty profound ways.
It definitely gets a little fuzzy down there.
To say the least.
And one of the things that I find most fascinating is the concept of wave-particle duality.
Oh, yeah. The idea that light and even matter can act like both waves and particles.
Exactly. It's like they can't decide what they want to be.
Right. It's one of those fundamental concepts in quantum mechanics that's just so counterintuitive.
Because in our everyday experience, things are either waves or particles.
Right. We think of ocean waves spreading out
And interfering with each other.
and particles as these tiny little points.
But in the quantum world, those distinctions get blurred.
It's a completely different set of rules down there.
And Greene describes this famous experiment that really highlights this duality.
The double slit experiment.
Yeah, it's like a magic trick that reveals the hidden nature of reality.
It's a classic experiment that has baffled and inspired physicists for decades.
So how does it work?
Imagine you shine a beam of light through two narrow slits cut into a barrier.
Okay.
And behind the barrier is a screen where you can observe the pattern of light that passes through.
Got it.
Now, if light were just a wave...
You'd expect to see an interference pattern on the screen.
Exactly, alternating bright and dark bands.
Caused by the waves interacting with each other.
Right.
And that's exactly what happens, right?
It is even when you dim the light so much that only single photons are going through the slits one at a time.
It still creates that interference pattern over time.
Like each photon is going through both slits at the same time.
And interfering with itself.
Exactly.
But how is that even possible?
That's the paradox. How can a single particle go through both slits at once?
Right. It's like it's somehow spread out like a wave.
Exploring all possible paths.
So it's like a tiny quantum multitasker.
Kind of.
But then we also observe light acting like discrete particles.
Right. So how do we reconcile those two things?
Yeah. Is there a way to make sense of it all?
Well, one way to think about it is through probability.
Okay.
In the quantum world, we can't say for sure where a particle will go.
Right.
We can only talk about the probability of finding it in a particular location.
So it's all about chance.
In a way. And those probabilities are determined by wave-like functions.
So the wave function doesn't tell us exactly where the particle is,
No.
but where it's likely to be.
It's like a map of possibilities.
Not a fixed trajectory.
Right.
And when the wave function goes through those two slits,
It's splits.
with each part going through a different slit.
And then those two parts interfere with each other, creating that pattern on the screen.
So the photon is exploring all those paths simultaneously.
And the interference pattern is the sum of all those possibilities.
But when we actually measure the photon's position,
Yeah.
it collapses into a single point.
And acts like a particle.
So the active measurement forces the wave function to collapse.
Exactly.
It's like the photon chooses a path at the moment we look at it.
That's one way to think about it, although it's important to remember we're talking about probabilities, not conscious decisions.
Right.
The act of measuring something fundamentally changes the system.
It forces it to go from multiple possibilities to one definite outcome.
That's a key idea in quantum mechanics.
And then there's Heisenberg's uncertainty principle,
Ah, yes, another mind-bending concept.
which says that we can never know both the position and momentum of a particle with perfect accuracy.
The more we know about one,
The less we can know about the other.
it's like there's a fundamental limit to how much we can know about a particle.
And that's not just because of our instruments.
Right, it's built into the fabric of reality at the quantum level.
It's not about our lack of knowledge.
It's about the inherent nature of these quantum systems.
So, particles don't have well-defined positions and momenta until they're measured.
That's the idea.
It's like the act of observation brings those properties into existence.
And this uncertainty has huge implications for our understanding of cause and effect.
Because in the classical world, we assume that every event has a definite cause.
Right, A leads to B.
But in the quantum world, things are much more probabilistic.
It's not so clear-cut. There's randomness woven into the fabric of reality.
So we can't always trace a direct line from cause to effect.
Right.
It's both exciting and a little unsettling.
I agree. It's liberating because it suggests that the universe isn't just a deterministic clockwork.
Right. There's room for possibilities.
But it's also unsettling because we like certainty.
We like to know what's going to happen.
It challenges our desire for predictability.
It definitely requires a shift in our thinking.
But that's what makes exploring these ideas so fascinating.
It forces us to confront our assumptions about the world.
And to embrace a new way of seeing reality.
And this new way of seeing reality gets even more challenging with the concept of quantum entanglement.
Yes, one of the spookiest phenomena in quantum mechanics.
Entanglement, it's when two particles are linked together.
In such a way that their fates are intertwined.
No matter how far apart they are.
It's like they're connected by an invisible thread.
That transcends space and time.
So even if you separate these particles by huge distances,
Millions of light years even.
measuring one instantly influences the other.
Like spooky action at a distance, as Einstein called it.
And it's been experimentally verified many times.
It's real.
It violates our classical intuition about locality.
The idea that objects can only be influenced by their immediate surrounding.
Right. It seems like there are connections in the universe that go beyond our normal understanding of space and time.
So entanglement suggests that there's more to the universe than we can see or even imagine.
And it has potential implications for technologies like quantum computing.
It's clear that the quantum world is a place where our everyday intuition just doesn't apply.
Where particles can be in multiple places at once.
Where uncertainty reigns.
And where spooky connections defy the limits of space and time.
It challenges us to expand our understanding of reality.
And to embrace the profound strangeness and beauty of the universe at its most fundamental level.
And as we continue our journey through the elegant universe, we'll see how these quantum mysteries connect to the quest for a unified theory of the cosmos.
A theory that could unlock the secrets of the universe's origin and its ultimate fate.
Welcome back to our deep dive into Brian Greene's The Elegant Universe. We've been exploring some pretty mind-bending ideas in physics.
We have from the quantum realm to the search for a unified theory.
A theory that could explain the universe at its most basic level. And in this final part, we're going to dive deeper into string theory.
Yeah, a pretty fascinating and controversial idea.
It is one that tries to bridge that gap between general relativity and quantum mechanics.
Right, and it might even offer a glimpse into the very fabric of reality.
String theory really pushes the boundaries of what we thought we knew about the universe.
It does.
It says that the fundamental building blocks of everything are not point-like particles, but these tiny vibrating strings.
And it suggests there are more spatial dimensions than just the three we experience every day.
It's a lot to take in.
It is. It definitely challenges our conventional view of the universe.
But Greene explains that it's a theory driven by mathematical elegance and the desire to answer some of the biggest questions in physics.
Like how to reconcile gravity with quantum mechanics.
Right. We talked about how those two pillars of modern physics just don't seem to get along when we try to describe extreme situations.
Like black holes or the Big Bang.
Exactly. So how does string theory address this conflict?
Well, in string theory, gravity isn't this mysterious force acting at a distance. It comes from the interactions of these vibrating strings.
Okay.
Just like different vibrations of a guitar string produce different notes, different vibrations of these fundamental strings give rise to the different forces and particles we see.
Including gravitons.
Yes, the hypothetical particles that carry the force of gravity.
So string theory brings gravity into the quantum world.
Exactly, allowing us to describe it in the same language as the other fundamental forces.
A pretty big deal.
It is. It offers a path toward a unified theory of physics, a theory of everything,
A theory that could explain the universe at all scales.
from the subatomic to the cosmic.
But string theory also introduces some pretty wild concepts like those extraspatial dimensions.
Yeah.
Our everyday experience is limited to 3 dimensions: length, width, and height.
Right.
So how can we even imagine these extra dimensions?
Well, Greene uses a helpful analogy.
Okay.
Imagine a garden hose stretched out far away.
Okay.
To us, it looks like a one-dimensional line.
Got it.
But to a tiny ant crawling on its surface, the hose is a two-dimensional world. The ant can move forward and backward, but it can also move around the hose's circumference, a dimension that's curled up and invisible to us from afar.
So our universe might have these hidden curled up dimensions too.
Exactly, adding a whole other layer of complexity to reality.
And just like the ant's perception of the hose changes as it explores that extra dimension.
The properties of particles in string theory are influenced by these unseen dimensions.
Leading to a deeper understanding of the universe's structure.
That's the idea.
But how do these extra dimensions affect our understanding of gravity?
One of the key insights of string theory is that gravity is weaker than the other forces because it can leak into these extra dimensions. It's like a water balloon with tiny holes.
The water representing gravity.
Right. It can escape through those holes into other dimensions, making it seem weaker in our three-dimensional world.
So these extra dimensions aren't just some theoretical idea.
They have real implications for how gravity behaves.
And they also play a role in string theory's attempts to explain black holes.
Definitely one of the most mysterious objects in the universe.
These objects so dense that nothing, not even light, can escape their pull.
Exactly.
So how does string theory help us understand them better?
Well, one of the biggest puzzles in physics is the singularity at the heart of a black hole.
That point of infinite density where the laws of physics break down.
Right. String theory suggests that those singularities might not be as singular as we thought.
Okay.
Instead of infinitely dense points, they could be fuzzy regions where space-time is highly curved, but not infinitely so.
So string theory smooths out the rough edges.
Providing a more complete picture of what's happening inside black holes.
But what about all the information that falls into a black hole?
Right. Doesn't it just disappear?
That seems to violate some pretty fundamental laws of physics.
That's the black hole information paradox, and string theory offers a possible solution.
Which is
The holographic principle.
holographic principle. That sounds like science fiction.
It's a mind-bending idea, but it's based on some deep mathematical connections found in string theory.
Okay.
It suggests that the information within a black hole isn't lost. It's encoded on its event horizon, that boundary beyond which nothing can escape.
So like projecting a 3D image onto a 2D surface.
Exactly, preserving all the information but in a different form.
So the information isn't destroyed, it's just transformed and spread out.
And this holographic principle has led some physicists to speculate that our whole universe might be a kind of hologram.
Whoa, a projection of information encoded on some distant boundary surface.
It's a radical idea.
It really makes you question what reality even is.
It does. It highlights the deep connection between space, time, and information that emerges from string theory.
So string theory is clearly a powerful and thought-provoking idea.
It is.
But it also faces some challenges
Like the fact that it hasn't yet made any testable predictions.
that could be confirmed or refuted by experiments.
That's right. The energy scales needed to directly probe string theory are way beyond our current technology.
But physicists are still looking for indirect ways to test the theory.
Looking for subtle signs in the cosmic microwave background radiation or in the behavior of particles at high energies.
So the search for evidence continues.
It does. But even if string theory doesn't turn out to be the ultimate theory of everything,
It has already had a huge impact on our understanding of the universe.
it has. It's given us new ways to think about gravity, quantum mechanics, and the interconnectedness of the cosmos.
And it's challenged us to expand our imagination and to consider the possibility that the universe is even more complex and amazing than we ever thought.
It's a journey of discovery that never really ends.
And Brian Greene's The Elegant Universe has been an incredible guide on this intellectual adventure.
It's taken us through some of the most mind-bending concepts in modern physics.
And it's left us with a sense of awe and wonder at the beauty and mystery of the universe,
It reminds us that science is not just about finding answers,
but about asking the right questions
embracing the unknown.
and pushing the boundaries of human understanding.
Exactly. It's a journey that I, for one, am excited to see where it leads us next.
Me too. Thanks for joining us on this deep dive into the elegant universe. We'll see you next time.
Make sure to subscribe and share this episode with your friends. We're constantly exploring new and challenging ideas, things that make you question what you think you know.
And we've included a purchase link for the book in the show notes, just for you. Keep those minds sharp and never stop questioning. Until next time.